Infrastructure as a code, which is also termed as IAC, has become increasingly important. This enables the organizations and teams to automate their cloud infrastructure management. Some of the popular tools in this segment include Terraform, Ansible, Chef, Puppet, and AWS CloudFormation. Most of these tools use declarative language like YAML or JSON to define the infrastructure code. As you know, even to deploy a sample web application or a database, you need multiple AWS resources and configurations. As the infrastructure needs are increasing, so is the infrastructure code. And this is leading to complex implementations where the infrastructure code is becoming difficult to maintain or update. AWS Cloud Development Kit, which is most often termed as CDK, tries to address these challenges by providing an ISE framework based on a familiar programming language like Python, Java, JavaScript, etc. As the name suggests, AWS CDK is offered by AWS, Amazon Web Services, and here is how Amazon defines it. It says that the AWS CDK lets you build reliable, scalable, cost-effective applications in the cloud with the expressive power of a programming language. The key here is, of course, the programming language. So instead of the declarative one, with CDK, you can use the programming language to build your infrastructure automation code. Developing the infrastructure code with programming language provides multiple benefits. You can use the programming idioms like parameters, conditions, loops, etc. to model your ISE code. You can leverage the object-oriented concepts like inheritance, abstraction, etc. to increase the overall maintainability of your code. You can use the CDK constructs already available with CDK to develop the ISE code. The constructs can create the dependent resources and default configuration for you. This can help to build your infrastructure code faster and in efficient manner. As you are using programming language, you can bring your best practices for the application development to develop your infrastructure code as well. You can implement the code reviews, unit test, source control, and the overall pipeline with this. CDK is integrated with the Construct Hub, which is an online registry for the CDK libraries. Developer community is building numerous CDK constructs focused on various use cases and publishing it to the Construct Hub. You can leverage these constructs to further speed up your development. An important thing to note here is that CDK framework is built on top of AWS CloudFormation, which means you get all the advantages CloudFormation already offers to you, which includes the automated infrastructure provisioning, faster deployments, reduced errors in deployments as they are automated, dependency management, rollback, and versioning. CDK currently supports 6 programming languages, including TypeScript, JavaScript, Python, Java, C# or .NET, and Go. When you're writing the infrastructure code, you can use the CDK constructs to provision the AWS resources. For instance, you can have the construct representing an S3 bucket, or you can have a construct representing an EC2 autoscaling group. These constructs can provision one or more AWS resources for you. For example, if I'm using an AWS autoscaling group, it will be automatically creating the launch template, security group, and the other required resources for you. You can define one or more CDK constructs inside a stack, which is a unit of deployment in CDK. All AWS resources defined within the scope of a stack are provisioned as a single unit. This also means that they can be updated or deleted together as one unit. A CDK application is a container for one or more stacks. The code for the CDK app gets converted into the respective CloudFormation templates. CloudFormation engine interprets these templates and provisions the required stacks and resources for you. CDK is built on Node.js, so you can install the CDK as one of the Node libraries. To work with CDK, you need to initialize the CDK application first. As we discussed earlier, CDK supports multiple programming languages. You can initialize the CDK code in either of these supported languages. This creates the basic code structure in the specified language. You will be building your CDK application on top of the initial code structure created as part of the initialize process. You will be leveraging the CDK constructs and utility classes in order to develop your CDK application. Once your CDK code is ready, the synthesize process will help you to transform this into CloudFormation templates. These templates will be picked up during the deploy process and the respective stacks will be created by the CloudFormation engine. At the end, the stack execution of CloudFormation will provision the AWS resources for you. CDK is based on Node.js, so please ensure you have the Node.js setup on your environment. At the time of recording, CDK is expecting Node version which is greater than 14.15. For the current version, please check the AWS docs. I have provided this link in the reference document. Depending upon the choice of your language, you need to ensure you have the required setup for it. In this course, as we are going to develop the examples in Python, this requires Python pip, which is the Python package manager, and the virtual environment installed on our machines. The other prerequisites for CDK is to have the AWS CLI, which we have already installed and configured. Once our prerequisites are met, we can go ahead and install the CDK. Before that, let's confirm the Node.js setup. I'll use Node version command for it. The command returns successfully. We are using Node v18+. As CDK is one of the Node libraries, I'll use Node package manager to install it. Please note that I'm installing CDK in the global space. I'm also using sudo just to ensure it does not run into any permission issues. Let's run the npm command. The command is successfully completed. Let's confirm the CDK installation. I'll use CDK version command for this, and it shows the current CDK version as 2.99. Now that CDK is installed successfully, let's configure it. For CDK to work, it needs a staging S3 bucket, IAM roles, and few other resources. To create these resources, you need to run CDK bootstrap command. The command throws error as we need to pass the AWS account and the region reference with this command. We can use AWS STS getCaller identity command to get the account details. Here it is. Let's run the bootstrap command again. Let me copy the account ID and paste it here. I'm using AWS region as US East 2. The command has started. This might take a few minutes. Internally, this command has created a CloudFormation stack, which is creating the required resources for CDK. CDK Bootstrap is completed now. I would encourage you to look into the AWS CloudFormation console and see what resources it has created as part of the Bootstrap process. This consists of the IAM roles, policies, S3 bucket, etc. With this, we have successfully set up the CDK on our local environment. To start, let's initialize our application first. I'm going to create a new directory here. I'll name this first CDK app. I'll change the working directory to the newly created one and run the CDK init command. The argument it takes is the template. I'm going to provide the default template, which is app. The command accepts the language option. I'm going to specify this as Python, which means our CDK implementation will be based on Python. The command is completed successfully. Here it provides a set of useful commands: CDK ls, CDK synth, CDK deploy, diff, etc. We will be using most of these commands very shortly. Here are some additional notes. As it says, it's a blank project for our CDK development with Python. CDK.json has been created with the execution configuration. We will look into this soon. Then it talks about the Python virtual environment, which is automatically created for you. You can activate the virtual environment by running this command. Let's pick up this command and run it on our terminal. As you can see, it has activated the virtual environment for us. The notes also talk about installing the required dependencies. Here is the command for it. I'm going to copy this. If I look into the file it is referring, you can see it has entries for AWS CDK library and the constructs library. Let's run the command, which is going to refer this file and install the required AWS CDK libraries and the dependencies for us. The command is completed. As you can see, it has successfully installed the required libraries for us. The command has generated a basic structure for us. Let's go and explore it out. I'll use my Visual Studio Code to do that. If you do not have the Python extension for it, please go ahead and install this. This will really help in developing the code for us. Optionally, you should also install the AWS Toolkit, which provides the easy interface to interact with the AWS services. As you can see, it has 3 folders inside the CDK application. The first one represents the virtual environment. In the bin folder, you have the executables. And in the lib folder, it has the dependent libraries. For instance, here is the AWS CDK library listed, and these are the other libraries referred in the code directly or indirectly. Here is the core application folder and the test folder. Gitignore is created by default, which we will use eventually. cdk.json is the primary reference file for the CDK command. If you look inside this, it contains multiple things. The most useful thing here is the command to run the CDK app. The CDK command triggers the Python 3 command with the app.py file as the argument. App.py is available here. This provides an entry point for the CDK application. It's importing OS module by default. Then it's importing the AWS CDK, which is available through the site packages. And then it's referring to the local folder called first CDK app. And the file inside this called as first CDK Apps Stack. From this file, it's importing the first CDK Apps Stack class. Here it's creating the CDK app instance and the first CDK App Stack instance. This accepts 3 parameters. First is the scope, which is the CDK app itself. The second parameter is called as construct ID, which helps in naming the AWS resources and the identifiers. The third parameter provides the option to pass the additional configuration, which is not needed as of now. If we go inside the code representing our CDK stack, here is the file. From AWS CDK, it's importing the stack construct. And from the constructs library, it's importing the core construct class. Here it is defining the first CDK app stack, which is of type cdk.stack. This is the constructor. It has the self-reference, the scope parameter defined with the type construct, construct ID, which is of type string, which we have defined as first CDK app stack here. And then this is the optional key value arguments. Here we are calling the super to initialize any object present up in the hierarchy. Now that we understand the core components of our CDK application, let's extend this with a custom AWS resource. Before we add our resources, we need to fix these warnings. Visual Studio Code is unable to understand the site packages like AWS CDK and constructs. To fix this, click on the quick fix, select a different interpreter, and we are going to select the interpreter available in the virtual environment. As you can see, we are good with the warnings now. They are not visible anymore. Another thing we need to confirm is that the code generated by CDK init is working fine. For that, we'll do a sanity check with the CDK ls command. CDK ls lists down all the stacks defined in the CDK application. To run the CDK commands, first we will activate the virtual environment. By running this, let's run CDK ls now. And this returns the stack ID successfully. In our first CDK app, we will be provisioning a S3 bucket. For this, I'll use the S3 construct library available inside AWS S3 module. And this contains the bucket construct. The first parameter for the bucket is scope, which in this case is the stack itself. So we will use the self. And this ensures that the bucket will be provisioned as part of the CDK stack represented by this class. Second parameter is construct ID. We will give this value as my first bucket. CDK will use this value to manage the lifecycle of this construct and also to generate the names and identifiers. And the third parameter represents the key value arguments, which can be used for construct configuration. For demonstration purpose, I'll be using the version property of the S3 bucket here, which defines whether the objects inside S3 should be versioned or not. This accepts the Boolean value, and I'm setting this as false. With this, our sample code is ready. As discussed earlier, CDK converts a code into the CloudFormation templates. You can use CDK synth command to do this. Let's run this command. It has returned a successful response, which is the generated CloudFormation template based on our CDK code. If you see this response closely, here is the AWS S3 bucket definition. A better way to browse through the template is to go to cdk.out folder. This folder keeps the generated templates and other artifacts. Here is the template in JSON format. Here is the bucket reference. This is the CloudFormation type. There are some default values which CDK is setting on our behalf. It creates CDK metadata, which CDK uses internally to keep track of the resources. The synth command also notifies us if there is any error in the CDK code. As it has returned the CloudFormation template, this means our code is good to go for the deployment. To deploy the CDK code, we will use CDK deploy command. The command is started. Behind the scenes, this has triggered the CloudFormation stack. Here it shows create in progress. It shows that S3 bucket is in progress, which is part of the CloudFormation stack, which is also in progress state. This will take a few minutes, so let's wait for it to finish. The command is completed successfully. We are going to validate this with the help of AWS console. I'm signed in to my AWS console, and this is the AWS CloudFormation page. I can see our stack for CDK Apps Stack. It's in create complete status. If you click this and go to the resources tab, here is the construct ID we provided for our bucket. It's in create complete status. If I click on it, it has created the bucket, and here is the reference for it. Additionally, it has created the CDK metadata as well. If I click on the bucket reference, we are in the S3 console, and here is the generated bucket. CDK has automatically given a unique name to it, which is a combination of our stack name, construct ID, and a random hash value. We haven't pushed any objects yet to this bucket, so it shows no objects here. Let's check the properties. You can see here is the versioning, which is showing as disabled. This is how we configured our bucket. Here is the set of tags it has created automatically: stack name, stack ID, and the logical ID. For the other properties, it has either automatically set the default value or has been left blank as they are optional. With this, we are able to successfully provision an S3 bucket with the help of our CDK code. I'm back to the code editor. Here is our first CDK stack. For the sample modification, I'll update the version parameter as true for our newly defined bucket. I'll save the file and run CDK synth to ensure our code is all good. The CloudFormation template is generated successfully, which means I can go ahead and deploy the application. Please note that when I run CDK deploy, it also executes CDK synth command for you. I'll run the CDK deploy command now to push the changes. The command has started again. Now it shows update in progress as our stack is already existing. As you can see, our command is completed now. Let's go to the AWS console and confirm it. We are at the AWS CloudFormation console and it shows that the update is completed. If you click on Stack and Events, you will see that it shows Create Complete Event, which corresponds to our first CDK deploy run. And then the update process started. And here is the event representing our update completed. If we go to the Resources tab and click on the bucket reference, here is our S3 bucket. If we click on Properties and look at the bucket versioning property, you can see that the versioning configuration is updated. It's in enabled state now, which means any object we create and update, S3 will maintain all the versions for that object. With this, we are able to modify our CDK code and push the changes to the AWS resources successfully. Last but not the least, we will see how we can delete the CloudFormation stack, which will also delete the associated resources. I'll use CDK destroy command for it. Before I run this command, I want to add two more construct properties as part of the key value arguments. The first one is auto delete objects, which we will set as true. So a bucket can have multiple objects. When the delete request is made, by default, it does not delete the child objects from it. And this can stop the bucket deletion. By setting this value as true, we tell S3 to delete the child objects when a delete request is made to the S3 bucket. The second property is removal policy. By default, it has the value retain, which means when the CloudFormation stack is deleted, it does not delete the storage resources like S3, DynamoDB, etc. By setting the removal policy as destroy, we override this behavior and CloudFormation can delete the bucket as well. The possible values are available in the AWS CDK libraries as enum. So I'll import it directly instead of this statement and then access it here directly. I'm going to update our current stack with these new parameters. Once updated, I'll be able to run the CDK destroy command. If I run it now, as the removal policy is not set, it's not going to delete the bucket. I'll use CDK deploy again to update the bucket properties. The command is completed successfully. Now we can run the destroy command. It's asking me to confirm this, which I just did, and delete is in progress now. Let's wait for this to finish. As you can see, our CDK stack is showing as destroyed. Let's confirm it. We will go to the AWS console. Here is the S3 bucket page opened. Let's refresh it. And it says that the bucket is not found. If we go to the bucket list, our bucket is missing here as well. If we go to the CloudFormation page and refresh this, it shows that the bucket is in delete complete status. If we click on stacks, our stack is not visible too, as it shows only the active CloudFormation stacks. A CDK construct represents a cloud component which encapsulates everything AWS CloudFormation needs to create the required AWS resources. For instance, while developing our first CDK application, we used the S3 CDK construct, which helped us in creating the AWS S3 buckets. Another example of CDK construct is the CDK stack, which helped in creating the CloudFormation stacks for us. What we used for our first implementation is just one type of CDK constructs. In total, CDK offers three different types: L1, L2, and L3. As we move from L1 to L3, the level of encapsulation increases with these constructs. Don't get bogged down by the term encapsulation. This simply means that as the encapsulation increases, so is the richness of these constructs. They offer more and more features and makes it easier for you to create the AWS resources. L1 constructs directly represent all resources available in the AWS Cloud Formation. You can say it's a one-to-one mapping with the Cloud Formation definitions. For instance, the CFN bucket construct, which is available in AWS S3 module, is equivalent of AWS S3 bucket resource type in the Cloud Formation. The L1 constructs are typically named with the prefix CFN. When you use L1 constructs, you configure all the resource properties as required by the AWS Cloud Formation definitions. L2 constructs provide additional features on top of L1 so that you do not need to worry about all the configurations about the AWS resources they represent. This can include the default values, convenience methods to enable rich features, or the glue logic to connect the dependent resources. For instance, the bucket construct, which is of type L2, available with the AWS S3 module, provides a convenience method add lifecycle rule. This helps in adding a lifecycle rule to the AWS S3 bucket. There are many other default values and utility methods associated with the S3 construct. L3 constructs provide further abstraction to this and are typically used to define the patterns on AWS. For example, the application load balanced target service construct available inside AWS ECS patterns is an L3 construct and represents an architecture that helps in implementing the AWS Fargate cluster with application load balancer. Another such construct is Lambda REST API available inside AWS API Gateway. This helps in defining the APIs based on AWS API Gateway and AWS Lambda functions. L3 constructs are designed to help you implement the recommended best practices patterns, which often involves multiple resources and the logic to connect them together. Let's talk about how the constructs look like. Irrespective of the type of CDK constructs, directly or indirectly, they extend the construct base class, which further implements the iConstruct interface. When you initialize any construct, you pass three parameters to them. The first parameter is scope, which represents the construct's parent or the owner. For instance, if you're defining a bucket inside a CDK stack, then the stack will be the scope of your bucket construct. The scope could be either a stack or any other construct. The second parameter represents an identifier, which serves as a namespace for everything that's defined within the scope. It's also used to generate unique resource identifier. For instance, the bucket name or the Lambda function name. The value of this parameter must be unique within a scope. Key value arguments, which is the third parameter, is a set of key value pairs that define the construct's configuration. For instance, while defining the CDK bucket, you can specify the versioning configuration, encryption configuration, etc. with the help of these key value arguments. The constructs are designed with the concept of sensible defaults, which means you need to provide minimal configuration while provisioning any AWS resource through the CDK constructs. The key value arguments provide you the full control over the resource configuration, which you can leverage to customize your resource definitions. The construct typically exposes a set of methods and attributes. Once you initialize the CDK construct at your end, you can leverage them to interact with the construct. You can also pass around the construct reference in the CDK application and consume it like any other programming object. App is a spatial CDK construct which represents the entire CDK application. We have already used it in our previous examples. The recommended way to use this is by having a single instance of it and attach one or more stacks to it, which can further contain one or more CDK constructs. The app construct provides the root context for all the stacks and to the child constructs. When the construct tree is generated, this object sits at the root of it. The app instance or object is having a one-to-one relation with your CDK application. Technically, you can create multiple app instances, but it does not serve any purpose. This diagram represents the sequence of events which take place when you run the CDK deploy command. As you can see, the CDK app contributes for the phases including construct, prepare, validate, and synthesize. Let's discuss each of these phases to understand the purpose of app construct better. Before it reaches the construct phase, we need to define the CDK application. We have already used the app construct in our previous examples, but let's look at this closely. You would define an app instance in your program's entry point. Typically, the app construct does not require any initialization arguments. Though it's a construct, but you do not pass any parameters to it like scope, ID, etc. This is because the app construct by default becomes the root construct. When you define a stack, which is another construct, you can pass the app object as the scope of it. As I said earlier, you can add multiple stacks with the same app scope or context. These stacks become the child constructs of the app object. During the construct phase, your code execution starts. This instantiates all the defined constructs. This includes the app, stacks, and other child constructs and links them together in the form of a construct tree. Prepare phase was previously used to make modification to the constructs when they get ready for the synthesis. This phase is deprecated now, so let's skip this. In this phase, all the constructs in the construct tree are traversed and get validated. All the constructs have the capability to validate themselves by implementing the validate method. This method provides a confirmation that the construct is in a good state and can be deployed correctly. If any validation failures happen, you get notified during this phase. This phase is responsible to generate your cloud artifacts. Primarily, AWS CloudFormation templates are the output of this phase. Other artifacts include the Docker images, application bundles, and other deployment artifacts which are required to run your business applications. This phase is triggered by a call to synth method on the app construct. Again, it traverses the app construct tree during this phase and invokes the synthesize method on all the constructs. In this phase, the CDK toolkit takes the cloud artifacts which were produced by the synthesis phase and pushes them to your AWS environment. Once done, this starts the CloudFormation deployment, which in turn provisions the AWS resources defined in your CDK application. Please note that the CDK app has already finished and exited before the deployment phase starts. This means your app instance is not referred anymore during this phase. When we talk about CDK environment, we are referring to the AWS environment, which primarily consists of the AWS account and AWS region, where the CDK stacks will get deployed. All the CDK stacks get associated with an environment before they get deployed. You can deploy different stacks to different environments within a single CDK application, or you can associate multiple stacks to a single environment. You can define the mapping based on your infrastructure needs. You can either let the CDK identify the environment automatically for you, or you can specify this explicitly. When the stack environment is set implicitly, it's also termed as environment agnostic stack. In this case, the AWS environment is identified at the time of deployment. When you run the CDK deploy command, the CDK CLI uses the AWS CLI profile to determine the environment. You can pass the specific profile along with this command. If no profile reference is passed, it automatically picks the default profile for you. Alternatively, you can explicitly specify the environment in the CDK code itself. When you're instantiating a CDK stack, you can pass the environment parameters as part of the stack properties or the key value arguments. You can also configure your CDK code to pick up the environment based on the local environment variables. You can create the environment variables on the machine where the CDK deploy is going to be run. This implementation is also a type of explicit environment mapping. Comparatively, this approach is more configurable than putting the values directly in the code. Also, this does not create any coupling with your AWS profile, as this was the case with environment agnostic stacks. Most of the time, you need to provision multiple AWS resources as part of a software development. An AWS resource might depend on another AWS resource for multiple reasons. For instance, Lambda function needs IAM role to access other services, or it needs the reference of DynamoDB to persist the data, etc. In a typical CDK application, there could be multiple such scenarios where you need the reference of another resource to make it work. As CDK application is developed with a programming language, referencing resource is comparatively a lot easier. We already discussed that AWS resources are represented as constructs in the CDK application. You can refer an AWS resource from another resource in the same manner you will be referring to any other object in the code. For instance, here is my sample ECS stack. I've created a VPC construct here and I'm passing it as one of the keyword arguments while creating the ECS cluster. We just discussed if the target AWS resource is defined, you can directly create a reference for it. There could be cases when the resources are defined outside of your CDK application. This might be created by some other ISE code or the manual process itself. In this case, you can access a resource through the proxy object. For instance, I'm creating the ECS task definition and I need to provide a task execution role. As I already have the IAM role created for it, I'm creating a proxy role object here and passing its reference to the execution role parameter. I've used a static method from role ARN of role construct here. There is another similar method from role name available with the role construct, where you can create the proxy role object with a name. Most of the CDK constructs provide such utility methods to refer to the existing AWS resources. Please note that when you create a proxy, the external resource does not become a part of your CDK application. What it means is that if you make any changes to the proxy object, it does not change the behavior of this resource. We already discussed about defining multiple stacks within the same CDK application. There could be scenarios where you need to refer a resource present in another stack. And in this case, you can refer the other resource with the reference of an enclosing stack. For instance, I'm creating an ECS task definition here, and I'm using self keyword to associate this definition as a stack class attribute. When another stack needs to refer the task definition, it can get hold of stack class reference first and then retrieve the task definition as a class attribute. When an AWS resource is referred from another AWS resource, you might need to ensure the API permissions. For instance, if an EC2 instance is dependent on an S3 bucket, the role attached to EC2 instance should have the permissions to call the S3 APIs. Many AWS constructs offer grant methods that you can use to grant permissions to work with the resource. With this, you do not need to manually create the IAM permission statements. For instance, here is my S3 bucket, and I want to ensure that my EC2 instance has the right permissions to access S3 APIs. To enable this, I'm using grant read write method of the bucket construct. Typically, there are multiple grant methods available with any construct. As you can see with S3, you can use grant read write, grant delete, etc. to provide the required API permissions. Network access is another thing to ensure when you are referring another resource. For instance, if one EC2 instance needs to connect to another EC2 instance, EC2 instances should have the right set of security group, inbound and outbound rules. Resources that establish or listen for connections, such as EC2 construct, have a connections attribute. This is of type connections, which is a utility class and providing methods to allow the traffic flows. As you can see, it has multiple allow methods, including allow from, allow to, and many others. These methods automatically configure the required network access with the help of security groups. Tags help you assign metadata to your AWS resources. Each tag is a simple label consisting of a key and an optional value. Implementing tagging across AWS resources can make it easier to filter and search for them, monitor the cost, monitor the consumption, and manage your AWS environment. In CDK, you can tag the CDK Constructs, which internally tags the AWS resources. When a tag is applied to the construct, CDK applies the tag recursively to all the children of the construct. For instance, if you're applying the CDK tag to your stack, CDK will apply the tags to all the constructs defined inside this stack. If any of the constructs in the stack is having children constructs, tag will be applied to them as well. And this will continue in a recursive manner. You can use tags class to apply the tags to your CDK constructs. Tags.off method helps in setting the root scope in the form of a construct to apply the tags. You can use the add method to apply the tag to the supplied scope construct and all of its children. Add method accepts a key and value as the primary parameters. Here is an example where we are adding a tag with the key microservice and value as my first service to the Lambda construct. There might be cases when the tag with the same keys are applied more than once on a resource. This will raise the conflicts as the CDK won't be able to decide which value to apply. CDK provides the option to associate priority while applying the tag with the help of tag properties. In case of conflicts, the priority values are compared and the value with the highest priority wins. By default, applying a tag has a priority of 100. If the priorities are not defined or they are same, then the tagging which is closer to the bottom of the construct tree gets applied. You can also use exclude resource types property while applying the tags. You need to specify the array of resource types with this property, and CDK will exclude these resources while applying the tags in the construct tree. For instance, in this example, the microservice tag will be applied to all the AWS resources except the resource which is of type IAM role. Similar to exclude resource types property, you also have the option of include resource types. With this, you can specify the types of resources you want to be tagged in the construct tree more specifically. In this example, the tag is applied to only the resources which have a type of AWS Lambda function. Tags class also provides remove method, which is used to remove the tags in the construct. This works similar to the add method. It removes the tags recursively in the construct tree. You can also apply the tags properties like exclude resource types, include resource types, and priority with this method. Assets represent the local files, directories, or the Docker images that can be bundled into the CDK applications. They can represent any artifact that the CDK application needs to function. For instance, the source code for the Lambda function, which we have already used for our sample implementations. CDK supports two types of assets, AWS S3 assets and the Docker image assets. S3 assets represent the local files and directories that the CDK uploads to the S3 buckets. And the Docker image assets, as the name describes, are the Docker images that the CDK uploads to the AWS ECR, Elastic Container Registry. You can define both the local files and directories as assets. CDK automatically packages and uploads them to the CDK S3 bucket. The asset construct is available through the AWS S3 Assets module. In most cases, you don't need to directly use the APIs in the AWS S3 Assets. Modules that support assets, such as AWS Lambda function, have utility methods to use asset constructs. For instance, Lambda construct provides the static method from asset to specify a directory or a zip file in the local file system to create an S3 asset implicitly. Docker image asset construct provides the capability to bundle the local Docker images as assets. This construct is available through the AWS ECR Assets module. CDK builds the Docker images from your local folder, which you set as the directory parameter. For instance, in this example, it's referring the My Image folder. It will look for the Docker file present inside this folder and will build the image based on it. Once the image is ready, it will upload this to the Elastic Container Registry. Aspects are a way to apply a set of instructions or logic to all the constructs in a given scope. For instance, let's say you want to ensure that all the buckets inside the given stack are encrypted. You can create an aspect with this validation and apply to a stack. This will ensure that all the validation for the bucket encryption logic is executed for all the children of the stack. During the synth process, if you encounter a bucket with no encryption, you can always throw an error, notify, or process some other logic. Please note that you can have one or more aspects associated to a CDK construct at any point of time. In one of the previous lectures, we talked about tagging the CDK constructs or the AWS resources. Tags utility class internally uses aspects to implement the tagging feature. Using aspects is very similar to tags, except that in this case, you need to define the aspect first. To create an aspect, you need to implement iAspect interface. Unlike the standard way to implement interface in Python, with CDK, you must use JSII decorator as shown here. Why we cannot implement the interface in a standard way? To understand this, we must understand the JSII first. JSII is the technology that enables the AWS Cloud Development Kit to deliver the polyglot libraries, which means the libraries in multiple languages like Go, Java, Python, etc. from a single code base. What this means is that all the CDK modules or the constructs which you consume in a typical CDK application are originally written in TypeScript. With the help of JSII framework, it gets converted into different languages as we talked about. With JSII in place, it becomes little restrictive in some cases to implement the Python idioms, and interface is one of such scenario. Traditionally, the Python developers implement the interface either implicitly or explicitly. With JSII type system, it does not support the structural typing, and the interfaces must always be explicitly implemented. To correctly implement the interface with JSII module in place, you first need to import the JSII module itself. Once you have it, you can import the interface which you want to implement, and then you can use a decorator to state that you are implementing the specific interface. Once you have the decorator statement, you can write the class in a very standard manner, and this will correctly register the explicit interface for this particular class. If you're interested in learning more about JSII, I'll share the link with you in the description and you can explore the module in more detail. Coming back to our aspect implementation, now that we understand the JSII, you can see we are using the JSII decorator here to implement the iAspect interface while creating the definition for bucket encryption aspect. The aspect interface has a visit method which accepts the node of any type. You can add your instructions inside the visit method. For instance, here we are adding the validation logic to check the bucket encryption and to capture the validation error. You have the complete flexibility inside the visit method. Depending upon the purpose of your aspect, you can read, you can modify the construct, or process any other information inside it. Once you have defined the aspect, you can consume it anywhere in your CDK code. You just need to call the Aspects utility class for it. Here is the syntax. This is very similar to how tags utility class is also consumed. First, you need to call the auth method to set the scope for the aspect. Then you need to apply the aspect object with the add method. Aspects in CDK employ the visitor pattern. When we call synth command, the CDK calls the visit method of the aspect and applies the aspect logic to all the constructs present inside the scope. CDK application is built in a programming language. This makes it as testable as any other business application. CDK applications based on Python are configured to use PyTest, which is a popular testing framework for Python. Additionally, CDK provides assertion utilities in each of the supported languages to help you test your constructs and applications more effectively. With CDK, you can write two kinds of tests. First, when you're dealing with the fine-grained assertions. In this, you can investigate any AWS resource and its properties generated as part of the CloudFormation template. For instance, you can check if the S3 bucket has a version property set as true or not. In second kind of test, you deal with the snapshots. These tests validate the synthesized CloudFormation template against a previously stored baseline template. In this case, you compare the whole template object and not any specific attribute of it. Creating tests with CDK assertions is pretty simple. CDK provides a template utility class which has multiple assertion methods. Here is the template API. As you can see, it's available inside AWS CDK Assertions module. Has resource properties is one of the most often used assertion method in this template class. It accepts type and then properties. For a given resource type, it helps you assert the property values in the generated CloudFormation template. There are other assertion methods available inside this class. This includes hasResource, which focuses more on the resource content rather than the specific property value. You have the assertion method to validate the parameter in the CloudFormation template. Here is the assertion to validate the output, mapping, or the condition in the CloudFormation template. Then you have the assertion methods to compare the resource count and the resource properties count. You can use any of these assertion methods to test your CDK applications. Apart from the assertion methods, it has multiple other utility methods which help you investigate the objects within the CloudFormation template for you. As I said, the hasResource properties assertion is most often used in the CDK application. Here is an example. Let's say you have a stack where you are creating a Lambda function, and in the test, you want to ensure the generated Lambda resource has the correct runtime. You can write the test where you can create a template instance representing the CloudFormation template for this stack and call its hasResource properties method. Inside this, you can provide the expected value for the runtime property. While running the test, if the runtime value matches with the expected value, the assertion will pass or else it will fail. Please note that you can include one or more properties in the same call to this method, which means I can check the Lambda handler reference, code, etc. in the same hasResource properties method call. Going back to the API, if you look into the documentation of hasResource properties, you will see that by default, it performs a partial match on the properties. Internally, it uses match.objectLike method for it. Match is another utility class available inside the assertions module. If we look into the API of it, here is the method which hasResource properties uses by default to compare the particular pattern of the property value. It says, for this method, the keys and their values must be present in the target, but the target can be a superset. And what does it mean? Is that if you look into the rendered CloudFormation template, let's say we are talking about the AWS Lambda function resource, and it has the code property which we want to assert. The code property has object as the value. Within this, there are multiple keys available with the multiple values. Even if you provide a subset of this object, let's say one key and one value, the match is going to be successful for you. This is the default matching behavior. The match class provides multiple other methods which you can use to customize your matching behavior. For instance, the object equals, which matches the object in an exact manner. The not method, which ensures this particular pattern is not existing. The exact method does a deep exact matching for any object. Array with can help you assert a subset of an array, whereas array equals assert the absolute array value for you. Any value will ensure that only the non-null value is present for any property. And with the absent, the match will pass only if the field value is not present. You can use any of these methods when you are using the has resource properties. So instead of using the value for the property, you can directly use the match method for it. Capture is another utility class available in the AWS CDK Assertions module. This helps you capture the values while matching the templates, which you can use to further compare the values in your test methods. With this, you do not need to provide the values in absolute sense to provide the assertion comparison. For instance, in the render template, if we have the AWS Lambda function, which has the tags value, and we want to compare with the tags value, which is present for the execution role, also available in the CloudFormation template. What we can do is we can capture the tags value within this function and then use it to compare it with the tags getting rendered in the IAM role resource as well. With this, I'm not providing any specific tags value here, but I'm just comparing the two values should be equal. So how do we use capture? Here is the example. It's an example template given. We can create a capture instance, and when we are using has resource properties, we can capture a specific property value. For instance, here we are capturing a value for the Fred property, which is available here. And you can retrieve the value with the as string method of the capture class. The class provides other methods to retrieve the other data types in your template. This includes as array, as boolean, as number, as object, as string. We already checked it out. Another interesting behavior of this class is if you look at this template closely, we have the Fred property available multiple times with the same type foo bar. In this case, when you are capturing the Fred property, it's going to create a collection of these property values for you. And you can iterate over these values with the help of next method, which works in a similar fashion as any other collection iterator works for you. That's it about the capture class. All the examples we are looking till now belong to the fine-grained assertion type. Unlike this, in snapshot testing, you compare the entire CloudFormation template. For this, you can use any snapshot plugin available with PyTest. Here is an example with CDK, which is one of such plugins. With this, you can retrieve the JSON object from the template and compare it with the snapshot, which you need to pass as a fixture to the test method. When the test is run first time, you need to run the test with snapshot update flag so that it creates the snapshot. For every subsequent run, the actual snapshot will be compared with the saved snapshot. There are few drawbacks with the snapshot approach. Snapshots can become outdated or irrelevant even if your CDK code changes are not significant. For instance, with the CDK upgrades, which might produce different format or structure for the CloudFormation template. In this case, you must update the baseline template if you encounter such change in the CloudFormation template.